Welcome to the lesson on the terms, symbols, and rules of geometric dimensioning and tolerancing. Upon completion of this lesson, learners will be able to identify and differentiate between the symbols used in GD and T, differentiate between the two main tolerance zone size modifiers, and explain and apply the two main GD and T rules. To understand GD and T, it is important to learn its language. This language is composed of both terms and symbols. There are also two rules used in GD and T. The following lesson will walk you through the most common terms, symbols, and rules using detailed images and explanations. Throughout this module and when reading technical drawings, you will encounter several GD and T terms. In a technical drawing, a feature is a general term applied to a section of a part. A feature can be a surface, a hole, or other parts of an object that require GD and T. It refers to the physical portion of the part. In the previous lesson, the term datum was introduced as a theoretical plane, point or axis used to measure a dimension on the part. A datum feature is a feature of a part that makes contact with a datum. A datum feature simulator is a surface or feature characteristic that simulates a datum plane or axis. A datum feature simulator, for example, can be the axis of a hole or slot. Material condition modifiers are found in feature control boxes and are used to refer to a feature in its largest or smallest condition. Maximum material condition, abbreviated as MMC, is the condition of a feature size that contains the maximum amount of material based on the tolerance limits of size. Differing from MMC, the least material condition, abbreviated as LMC, is the condition of a feature size that contains the least amount of material based on the tolerance limits. The next two slides include an example to better explain this concept. Maximum and least material conditions are concepts that can be very confusing. So, let's review an example. The image on this slide shows a top view of a block with a hole feature within it. The hole diameter is 1 inch with a tolerance of plus or minus 0.005 inch. The maximum material condition is the maximum amount of material based on the tolerance limits of size. Think of the material as the part material in terms of weight. Therefore, the most amount of material that the part, not the feature, can have will occur when the feature is the smallest. The next condition is the least material condition. Consider the same image as in the previous slide. LMC is the least amount of material based on the tolerance limits of size. Again, think of the material as the part material in terms of weight. Therefore, the least amount of material that the part, not the feature, can have will occur when the feature is the largest. In addition to the maximum and least material modifiers, the third material condition modifier is called regardless of feature size, abbreviated as RFS. RFS is often used to explain that a geometric tolerance applies to the feature within its size tolerance regardless of its size. Another tolerance zone modifier is statistical tolerance. Statistical tolerance, abbreviated as describes a dimension or tolerance that was established using statistical methods. It states that the part should be manufactured and its quality controlled using statistical process controls. It should be noted that statistical tolerance is used in ASME Y14.5 standards and not in the ISO standards. Other tolerance zone modifiers not covered in this module include projected tolerance zone, P, free state, F, and tangent plane, T. GD&T also develops tolerance zones. A tolerance zone is the space created by a tolerance. Tolerance zones are important when two or more objects, like a pin and a pinhole, are to be assembled. For these parts to be assembled appropriately, the pinhole will have to be manufactured to be slightly larger than the pin so that the pin can fit inside of it. A running or sliding fit occurs when the size of one part is always smaller than the size of its mating part. Look at the example at the bottom of this slide. The maximum acceptable size of the pin is 10.53 inches in diameter, and the minimum acceptable diameter for the pinhole is 10.56 inches. The intentional difference between these two parts is known as an allowance. Allowances are typically small, but they are necessary for proper assembly of finished parts. In this example, the minimum allowance in this design is 10.56 inches minus 10.53 inches, so it is 0.003 inches. This means that these two parts will have a minimum of 0.003 inches of space available in between the two parts when they are put together. A forced or interfaced fit occurs when two parts that are made at any size within their tolerances must be forced together. Because these two parts are designed to be such a similar size, it requires extra force to be able to put them together. Once these two parts are forced together, they create an almost permanent assembly of the two parts because they are so hard to separate. The maximum acceptable size difference between these two forced parts is known as a clearance. You can also think of clearance as the minimum size difference between two parts that you can still put together. When designing running fit parts, you would create an allowance between them that makes it so the parts will always be able to fit together and also come apart. When designing forced fit parts, you would create an allowance that is so small that it just meets the clearance so that the parts can be put together with some force but cannot be taken apart. For circular features in a part or surface, a radius or a controlled radius is identified. A radius is the distance from the center of a circle or arc extended to a surface. When an IR is used to identify a feature and is accompanied by tolerance measures, the tolerance zone is formed by two radii, which are the length of the tolerances. The image on the bottom of the slide illustrates this idea. The black arrow is the minimum radius, the white arrow is the maximum radius, and the gray semicircle is the radius tolerance zone in which the radius of that feature could fall. A controlled radius, or CR, works the same way when applied to a surface or feature. However, a controlled radius requires the finished product to have no flat areas or reversals, so in other words, it must be a perfect arc. There are a large number of symbols and terms used in GD&T. The symbols are created to resemble the requirements they identify. So, for example, the diameter symbol shows a line through a circle to represent the diameter of that circle. All of these symbols represent features and tolerances that identify repetitive features, diameters, radii, spot faces, and counterbores commonly used in technical drawings. Some of these symbols have been discussed in the module already, but some may be unfamiliar. There are two sets of symbols. The first set of symbols is the most commonly used in engineering drawings and in conjunction with geometric tolerances and other related dimensional requirements. These are the symbols you see listed here on this slide. The second set of symbols describes the geometric characteristics of features and can be seen on the next slide. Let's take a closer look at this table of geometric characteristic symbols. There are 5 types of tolerances that describe geometric characteristics. They are form, profile, orientation, location, and runout. Form, as the name suggests, describes the form of a part or feature. Profile tolerances describe the boundaries of a surface. Profile tolerances can be very complex as they can define a feature's size, orientation, and occasionally its location. Orientation tolerances describe the direction or orientation of a part or feature. Location tolerances describe the location and placement of a feature or part. Runout tolerances can describe straightness, profile, angularity, and other geometric characteristic variations of a feature or part. The first column of this table displays whether or not a type of tolerance uses a datum reference. Form tolerances never use datum references in the feature control frame. Profile tolerances sometimes use datum references. Orientation, location, and runout tolerances always use a datum reference. Position tolerances are the exception to this rule. On some occasions, a position tolerance may be used with a datum reference, but not always. The next few slides will describe each of these geometric characteristics in detail. The types of form geometric tolerances include straightness, flatness, circularity, and cylindricity. These describe the form of a part or feature. Straightness is a form geometric characteristic control that ensures a surface or axis adheres to a straight line within a specified tolerance. This control can be applied to various geometric features, including lines, edges, axes, and center lines. It guarantees that the targeted element maintains a linear path without significant deviations, ensuring precision in manufacturing and assembly processes. The figure shows the drawing of a cylinder where the straightness geometric tolerance is applied to the surface and an axis and a corresponding interpretation. When applied to the surface of this cylinder, the tolerance zone consists of 2 parallel lines. This zone must be less than the specified size tolerance. When applied to the axis of this cylinder, the tolerance zone is a cylinder. This zone may be greater than the size limits. The next form geometric characteristic is flatness. Flatness is defined as the condition of a surface to have all of its elements in one plane. This figure shows flatness applied to a surface. When flatness is applied to a surface, the tolerance zone consists of 2 parallel planes that are less than the size tolerance, that is 0.1 units apart. Flatness applies to the surface in all views. When circularity is applied to the circumference of a cylinder, as shown in this image, the tolerance zone consists of two coaxial circles, which are less than the size tolerance 0.1 units apart. Coaxial refers to circles or cylinders that share the same axis but may vary in shape. The last form geometric characteristic is cylindricity. The figure shows the cylindricity applied to the cylinder. In this case, the tolerance zone consists of two coaxial cylinders that are less than 0.1 units apart. Circularity tolerances are used to account for the roundness of circular parts or features. Cylindricity tolerances are often used when cylindrical parts or features must have both circularity and straightness. This can apply to cylindrical and spherical shapes such as cones, pins, and camshafts. Now, let us look at the next type of geometric tolerance, the profile tolerance. Profile tolerance is a geometric control that defines an allowable zone around a theoretically perfect surface or line. It simultaneously regulates form, orientation, and often location of complex shapes, ensuring the entire actual feature falls within the specified three-dimensional envelope. There are two types of profile tolerance: profile of a line, profile of a surface. Profile of a line is a geometric tolerance that controls the 2D shape of a linear feature within a specified tolerance zone. It defines allowable deviation from a theoretically perfect line profile in a single plane, applying to features like edges, contours, or cross-sections of parts. This tolerance ensures that the actual line falls within two offset curves that follow the nominal profile shape, effectively constraining the feature's form to match the intended design within the specified limits. The figure here shows a simple tolerance profile of a line applied to a feature of the part. 2 points, C and D, are identified as the zone to which the profile must be applied. In this case, the line is a semicircle with a radius of 3 units. The tolerance zones are two lines that match the shape of the feature between points C and D that are of the size tolerance, 0.1 units apart. Profile tolerances can also describe the profile of a surface. This figure shows the tolerance profile of a surface applied to a feature and to coplanar surfaces. Coplanar surfaces are surfaces that share a plane. When applied to a feature, the profile of a surface produces a tolerance zone that is two planes that match the shape of the feature between the indicated points C and D that are 0.1 units apart, as shown in the figure on the right. A dial indicator can also be used to ensure the tolerances. The maximum permissible reading on the dial indicator is 0.1 units. When applied to coplanar surfaces, the tolerance zone is made up of two planes that are the tolerance size 0.1 units apart, as shown in the figure on the left. One of the planes of the tolerance zone must be the datum referred to in the drawing. Applying a profile of a surface to coplanar surfaces ensures that those surfaces are as aligned as possible. Next, we will observe orientation tolerances. Orientation tolerance controls the angular deviation of a feature from its theoretically perfect orientation. It defines the allowable tilt or skew of surfaces, axes, or lines relative to a datum, ensuring proper alignment and fit of components in assemblies. The types of geometric orientation tolerances include angularity, perpendicularity, and parallelism. These specific tolerances allow designers and manufacturers to specify precise angular relationships between features. Angularity is a type of orientation tolerance that controls the angle between a feature and a datum plane or axis. It specifies the allowable deviation from a theoretically exact angular relationship applying to surfaces, axes, or other linear elements that should be at a specific angle. This tolerance defines a zone bounded by two parallel planes set at the specified angle to the datum, within which the entire controlled feature must lie. This figure shows angularity applied to a surface and a feature. When angularity is applied to the surface of a part, the tolerance zone consists of two parallel planes that are less than the size tolerance 0.1 units apart, as shown in figure on the left. However, when angularity is applied to a feature, the tolerance zone is a cylinder of the size tolerance of 0.1 units, as shown in figure on the right. In this case, the feature is a hole. Therefore, the axis of the hole must be within the cylinder, and the cylinder must be at 40 degrees from datum A. Perpendicularity is the next characteristic of the orientation type of tolerances. Perpendicularity specifies the allowable deviation from a theoretically exact 90-degree relationship between a feature and a datum plane or axis. It defines a tolerance zone bounded by two parallel planes perpendicular to the datum, within which the entire feature must lie. This control ensures that surfaces, axes, or other elements maintain a right-angle orientation within specified limits. The figure on the left shows perpendicularity applied to a surface and a feature. When applied to a surface, the tolerance zone is made up of two parallel planes that are less than the size tolerance 0.1 units apart, as shown in the figure on the left. Perpendicularity applied to a feature is shown in the figure on the right. The tolerance zone consists of two parallel planes that are no smaller than the lowest tolerance minus the size tolerance 0.1 units apart. In this case, these parallel lines must be 10.3 units apart. A go-no-go gauge that is 10.3 units wide, laid completely flat on datum, A can be utilized to determine if the part in the figure on the right meets specifications. The last of the characteristics of the orientation type of tolerances is parallelism. Parallelism is a geometric tolerance that specifies the allowable deviation from a theoretically exact parallel relationship between a feature and a datum plane or axis. It defines a tolerance zone bounded by two parallel planes that are themselves parallel to the datum, within which the entire feature must lie. This control ensures that surfaces, axes, or other elements maintain a consistent distance from the reference datum throughout their extent. Two parallel lines, planes, or surfaces are those that, when infinitely extended, do not cross or share a point. This figure shows parallelism applied to a surface. The corresponding tolerance zone is made up of two parallel planes that are 0.1 units apart and are also parallel to the reference to datum. Parallelism surface tolerances are used when a flat surface is required for the finished part. Parallelism can also be applied to the axis of a whole as shown in the figure. Parallelism applied to an axis controls the deviation of the axis from a perfectly parallel orientation relative to a datum plane or axis within a cylindrical tolerance zone. The corresponding tolerance zone is a cylinder of 0.1 units in diameter that is also parallel to the reference datum. The axis of the whole must be within this zone. The next types of geometric tolerance we will discuss are location tolerances. Location tolerances specify the allowable deviation of a feature from its theoretically exact position relative to one or more datum references. The geometric characteristics of location tolerances are position, concentricity, and symmetry. Position tolerance is a characteristic of location tolerance that is used to determine the position of a feature on a part. The image here shows a position tolerance applied to a cylindrical hole. Along with the position tolerance, all three datum planes are referenced in the feature control box. The tolerance zone for this feature is a cylinder of diameter 0.1 units that is located 8.5 units from datum B and 5.4 units from datum C. When a feature is repeated over a part, a single feature control box with a position characteristic may be applied to all. Concentricity is the next characteristic of the location tolerances. Concentricity means the two or more objects that share a center. This figure shows a concentricity tolerance applied to a feature. The tolerance zone is a cylinder of 0.1 units in diameter whose axis is on the datum axis A. To measure for concentricity, the median points of lines between two opposing features are measured. The two opposing features in this case are the inside walls of the hole in the specified feature. All median points must fit within the cylinder tolerance zone. The last characteristic of the location tolerances is symmetry. Symmetry is the equivalent of concentricity for non-cylindrical features. The figure shows a symmetry tolerance applied to a non-cylindrical feature. The tolerance zone is made up of two parallel planes that are 0.1 units apart and parallel to datum axis A. Symmetry also utilizes median points to confirm it meets requirements. All median points must fit within the tolerance zone created by the two planes. Let us now discuss run-out tolerances. Run-out tolerance is a composite tolerance that controls the total variation of a surface or feature during a full rotation around a datum axis. It applies specifically to cylindrical parts, particularly those that rotate, ensuring proper balance, minimizing vibration, and maintaining consistent performance. There are two types of run-out tolerances: circular run-out and total run-out. The first type of run-out tolerance is the circular run-out. Circular runout limits the circular deviation of a surface or feature at a specific cross-section perpendicular to the DOE datum axis. The image on the left shows a circular runout tolerance. Its tolerance zone is two coaxial circles, which are the tolerance zone 0.1 units apart. A dial indicator may be used to determine if the part is within the required tolerances. The dial indicator must show a reading of less than or equal to 0.1 units for the part to be acceptable. The second type of runout tolerance is the total runout. Total runout controls the entire surface deviation relative to the datum axis, combining circular runout for all cross-sections along the feature's length. The figure on the right shows a total runout tolerance applied to a circular feature on the part. The tolerance zone, in this case, consists of two coaxial cylinders of 0.1 units apart. Unlike circular tolerance, measurements on the total runout tolerance must be applied to the entire length and surface of the feature in question, not just at a specific cross-section. A dial indicator must be used to determine if the part meets specifications. The dial indicator must show a reading of less than or equal to 0.1 units for the part to be acceptable. Let us shift focus to a go-no-go gauge. This is an inspection tool used to check whether a part meets quality control requirements using its allowable tolerances. The figure here shows the upper and lower diameter tolerances of a cylinder inspected using a snap gauge, a type of go-no-go gauge. The top part of the snap gauge shows the cylinder meeting the upper tolerance. This means that the cylinder is smaller than the maximum allowable tolerance. The bottom part of the snap gauge shows the cylinder meeting the lower tolerance. This means that the cylinder is larger than the minimum allowable tolerance. If a cylinder's diameter is larger than the quality requirements, it will not fit either side of the snap gauge. If a cylinder's diameter is smaller than the quality requirements, it will fit on both sides of the snap gauge. But if the cylinder is the right size, it will fit in the top part of the gauge and will not fit in the bottom part of the gauge. In addition to the terms and symbols, GD&T follows two general rules that aid in the interpretation of characteristics. The envelope principle states that when only tolerances of a size are specified, the limits of the size of the individual feature also control the limits of the form. In other words, no element of the feature should go beyond the perfect form at maximum material condition. This principle is also referred to as Rule Number 1, the individual feature of size rule, or the perfect form at MMC. There are two exceptions to Rule 1, non-rigid parts and stock sizes. Rule number 2 states that RFS, or regardless of feature size modifier, applies by default when no other material condition modifier is specified. This ensures geometric tolerances are evaluated independently of feature size, maintaining consistent form, orientation, or location requirements regardless of manufacturing variations. We have reached the end of this lesson. In summary, identifying and differentiating the various symbols used in GD&T is the first step to understanding technical drawings. A technician must understand the difference between the maximum material condition and the least material condition for component and assembly drawings. Lastly, Rule Number 1 and 2 provide additional guidance to technical drawings and aid in the interpretation of characteristics. Thank you.